In these images, altering the time gain compensation sliders shows you the differing effects of different slider settings on the quality of the picture, where you're trying to achieve a uniform quality picture in the area of interest. Resolution is heavily related to frequency. The quality of the picture is related to the frequency of the ultrasound beam, with the general principle being that high frequency probes give excellent resolution but only a very poor depth penetration because of all the signal attenuation, and low frequency settings produce poor resolution but an excellent depth penetration because there's less tissue loss of the ultrasound energy as it goes through the deeper tissues. The depth setting you select when setting up your ultrasound machine should include the area of anatomical interest and should consider the effective frequency. The general principle is to use the highest frequency you possibly can that will still reach the depth that you want to interrogate. Generally, in medical ultrasound, these are the sort of frequencies in megahertz that are used for different applications. Resolution refers to the power of the ultrasound machine to discriminate between different reflectors at different depths and see these entities as separate tissues. The aim of high-resolution pictures is that the real anatomy depicted on the left should be represented as that in the screen on the right. With poor resolution, the four distinct anatomical entities on the left will be resolved as one amorphous blob when projected on the screen on the right. Axial resolution or vertical resolution refers to the ability of an ultrasound machine to differentiate between structures at different depths and is usually the most accurate part of an ultrasound machine's performance. Horizontal resolution, where structures at the same depth are differentiated as different, is normally of poorer performance and relies on a different ultrasonic principle. At the highest frequencies used, axial resolution in the more superficial tissues can get down to about 0.5 millimeters. The important issue when resolving axial resolution is the spatial pulse width, where shorter spatial pulse widths produce the most impressive axial resolutions. Ultrasound waves are generated not as continuous bursts of energy but as cycles of energy, typically in very short bursts, around 3 cycles per burst. So there'll be 3 or 4 wavelengths sent out. There'll be a big delay before a similar packet is repeated. During the delay, that gives enough time for the sound to enter the tissues and be reflected back, which means that with each burst of energy, the ultrasound machine then listens to see what's coming back. If you have so many cycles at such and such a frequency, then that will actually occupy a physical space within the tissues, and that is referred to as the spatial pulse width, which is symbolized by the black double-headed arrow on the right-hand diagram. The spatial pulse width is critical in axial or vertical resolution, and here we see a 3-burst ultrasound cycle with a fixed spatial pulse width approaching 2 different reflectors. As they approach the first reflector, some of the sound energy is reflected back, while the rest of the energy continues on to the second reflector. This is likewise reflected back, and what we have is 2 returning echoes separated by a gap, which means the ultrasound machine can resolve these as 2 different structures. If we put these 2 reflectors closer together, a different effect happens. Here we see a 3-cycle burst approaching 2 reflectors which are now much closer together. As they approach the first reflector, energy is reflected back off the first reflector. It then travels on to be reflected back off the second reflector, but this time the reflection coming off the deeper reflector manages to catch up or coincide with the reflector coming off the top one, which means these two reflections are merged into one, seen as one reflection, and does not allow the ultrasound machine to differentiate between these two as different structures. In order to be seen as distinct, the reflectors must be more than half the spatial pulse width apart. Otherwise the signals will combine to produce a single return rather than a double return. We can reduce spatial pulse width and therefore improve resolution with one of two methods. Either we can reduce the number of cycles in each burst, which will reduce the spatial pulse width as seen by the diagram on the left, or we can increase the frequency, which will shorten the spatial pulse width. Practically, it's very difficult to reduce the number of cycles below 3 because of the damping in the ultrasonic crystals. So generally, any increase in axial resolution using a reduction in spatial pulse width is manipulated through increasing frequency. Horizontal resolution at the highest frequencies is in the order of 1 millimeter, so it is less accurate than axial resolution, and it depends on the beam width being emitted by the ultrasonic probe, where the narrower the beam width, the better is the horizontal resolution. If we look at these series of diagrams, we can see a relatively broad beam width scanning across two reflectors, and if you look at the bottom of the screen, you can see the effect of this on the finished article in on the ultrasound screen. So as the beam moves across, there'll be a point where it is interacting with the first reflector, then it's interacting with both reflectors, then the last reflector, and finally it's moved away. The end result of this is that these two reflectors horizontally are seen as a single entity, which is what you see in the ultrasound screen at the bottom. So with that beam width, the machine has failed to discriminate between these two different structures. If we narrow the beam width, we can then have a period of time where the beam interacts with one reflector, there's a gap between the two with no reflections coming back, it interacts with the second reflector and then moves on. This is different because the end result now will be that the ultrasound machine can differentiate between these two different reflectors at the same vertical distance from the probe. The narrower the beam width, the better is the horizontal resolution. We can influence this by adjusting the focal point to coincide with the depth of the structures we're interrogating, and many modern ultrasound machines have one or more focus points that can be adjusted as little arrows on the side of the depth scale, and can markedly improve the image quality when manipulated to coincide with the depth of the nerve to be examined. Looking at this diagram, you can see that if the focal point of this beam were moved down to coincide with the depth of the structures of interest at 1, 2 and 3, we would get better axial resolution than as is currently shown, where they've got a wider part of the beam at their depth. So horizontal resolution is related to beam width, which is narrower with higher frequencies and narrowest at the focal point of the ultrasonic beam. So in summary, if we have 4 anatomical structures that are very superficial, it's likely the ultrasound machine will see all 4 entities as being separate, as shown in this picture. If we now move the structures to a deeper depth and have to use a reduced frequency, the first thing that would change will be the horizontal resolution. So now what you see on the screen looks like the structures are blurred horizontally. And if we go deeper still and have to further decrease the frequency, then all 4 structures will appear as a blob. This is simply a reflection of ultrasonic performance at increasing depth of tissue. There are a number of horizontal artifacts relating to shadowing and enhancement that can be improved by multi-beam technology. Multi-beam technology means that the same ultrasonic probe will interrogate the tissues from slightly different angles, such as here, and here, and these slightly different images are added together to produce a compound image which are generally of much better quality than the single beam technology. If your machine has multi-beam technology, it should invariably be switched on.